Related rates 2. Today we're going to look at triangle problems. Triangle problems are very common in related rates type questions, and they can take the form of many different scenarios, but the ones we're going to look at often include sliding ladders, airplanes, boats being pulled into a dock with a rope, building construction, just different things like that. Once you recognize that the question is a triangle problem, then most of the times they're going to work the same way. So this is sort of an overall category of a related rates type problem, and they tend to work pretty similarly. So let's take a look at them. Example 1 is a ladder problem. We have a 13-foot ladder that's leaning against a house when its base starts to slide away from the house. By the time the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. So the question is, how fast is the top of the ladder sliding down the wall at that particular moment? So if you remember in class, we were talking about the way you want to kind of set these up, and you want to figure out what it is you're being asked to find. So in this case, we want to find how fast the top of the ladder sliding down the wall. That's a rate, okay? We need to know when, and in this case it says at that moment, and that moment is going to be when the base is 12 feet from the house. And then we also want to know what we're given. Okay, so we're going to be given some information as well. All right, so let's start by drawing a picture just to really get a sense of what's happening. So here we have the side of a house, and that's the little roof, and there's the chimney, maybe a little window, okay, part of the door. All right, so there's the house, and we have a ladder that's leaning against this house, and this ladder is 13 feet long. Okay, so then what's happening is we have the base of the ladder start sliding away from the house, and it's doing at a rate of 5 feet per second. And that is a rate. Okay, so I'm going to call this base, I'm just going to call it B for base. And so this rate would be dB dt. And B is the distance the base is from the house. And at this particular moment, this is our when, it's 12 feet from the house. Okay, so when is when B, I should say B equals 12 feet. Okay, so that's our when the base is 12 feet from the house. All right, and we are given that the rate that that base is moving away from the house is 5 feet per second. You do need to ask yourself about whether or not that's a positive quantity or a negative quantity. And the way to tell is it causing our measurement to get bigger or smaller? Since we said that B was the distance the base is from the house, then as the base is sliding away from the house, the distance is going to get bigger, and so it does in fact need to be a positive quantity. Be careful, because they don't always tell you that it's a negative quantity when it should be negative. So, you know, this could have been that somebody was pushing the base of the ladder towards the house, and in that case, it actually would have been a negative rate because the distance the base is from the house would actually be getting smaller. But since we're getting larger, it's increasing, then our rate of change is going to be positive. Okay, we need to assign variables to the rest of our triangle, okay, because we're assuming that our house is straight up and down. It was built well, it's making a right triangle, the land has been graded well. So B is our base. I'm going to call the height that the top of the ladder is along the house here, that's going to be H, and I'm just going to call the length of the ladder itself L. Okay, So what we don't know is the height of the ladder, and we don't know the rate at which this will be sliding down, because as the ladder gets pulled out away from the house, the top of the ladder is going to slide down the house. Okay, so we have some things missing, but we'll fill those in. So our find is how fast is the top of the ladder sliding down. So that's how fast is this height changing, so we want to find dH dt. Now, it doesn't matter which letters you use. You get to assign your own letters. There's nothing in the problem that has them assigned. So you can use, A, B, C, you can use X, Y, Z, it doesn't matter, whatever you want to use. I just chose to use base, B for base, H for height, and L for ladder. Okay, so we are not given any equations in this problem. What we need to do is come up with the equation that relates all of these rates together. It's a right triangle. We got two legs and a side. I'm thinking Pythagorean theorem here. So I'm going to write b squared plus h squared equals L squared. So my base times my height equals the ladder. Okay, y'all need to go to 5th period now. All right, so let's work this out. So I am going to take the derivative of both sides of this equation, and I'm going to do it implicitly with respect to time. So 2b times dB dt plus 2h dH dt equals 2L dL dt. And then we just substitute everything in. So we have 2 times, and B is 12, and dB dt is positive 5, plus 2 times h. Well, we don't have h. However, we do have 12 as the base and 13 as the hypotenuse, so we can use our Pythagorean theorem to find h. So we would have h squared plus 12 squared equals 13 squared. And when you work all of that out, you're going to end up with h equals 5. So that would be 5 dH dt. And we don't have that. That's what we're trying to find. Equals 2 times L, which is the length of the ladder, which is 13, times the rate of change of the ladder. But the ladder is not changing size. So its rate of change is 0, because it's staying a constant 13 feet. And now we just start working everything out. Okay, so we've got 2 times 12 times 5, that would be, 120, plus 10 dH dt equals 0. And so when we bring the negative 120 over and divide by 10, we'll end up with dH dt equals a negative 12. And our units on that is going to be feet per second, and I'm getting that from the problem. Okay. All right, so dH dt is negative 12 feet per second. Now we want to write a little sentence answering the question, but we want to go back and read the question, because it says, how fast is the top of the ladder sliding down the wall at that moment? So we would say the top of the ladder is sliding down the wall at, and we're going to be very careful here, because the negative in our answer implies already that it is sliding down the wall. So we're not going to say it's sliding down the wall at negative 12 feet per second, because that would be a double negative and would imply it's sliding up the wall, I guess. What we're going to say is that the top of the ladder is sliding down the wall at 12 feet per second. And we have shown in our work that we got a negative, and then we've interpreted it as sliding down the wall at 12 feet per second. If the question had just said, how fast is the top of the ladder moving, then you could have said it's moving at a rate of negative 12 feet per second, but you would want to go on and say that that is causing it to fall down the side of the house. So you want to let us know what that positive or that negative means. Okay? All right, on to our next example. Okay, so this is a part B to the same problem. So we've still got the 13-foot ladder leaning against the house and all that. In A, we said how fast is the top of the ladder sliding down the wall, and we said it was sliding down the wall at a rate of 12 feet per second. Okay, so now part B says, at what rate is the area of the triangle formed by the ladder, the wall, and the ground changing at that moment? Okay, we just need to remember that at that moment, that was the moment when the rate that the ladder's moving is 5 feet per second away from the wall, and it is 12 feet from the wall. So I'm not going to draw the whole picture again, I'm just going to draw the triangle. So here B was 12, and dB dt was 5, and it was positive. H, we found H, excuse me, to be 5, and dH dt ended up being, I'm going to write it below it, negative 12. Now, this is a coincidence that the rates and the lengths are have switched places in these two quantities. That doesn't always happen, so that's just a coincidence, so don't read anything into that. And then L was 13, and dL dt was 0. All right, so at what rate is the area of the triangle formed by the ladder and the wall changing in the ground? Changing, okay? So we want area. So the formula for area of a triangle, a right triangle, is 1/2 base times height, okay? Make those capitals like I have in the problem. All right, so we have our formula. We have our find. We are going to find dA dt when B is 12 and dB dt is 5, and we are going to be given, well, I guess we were given dB dt, I'm sorry. So that's what we were given. Okay, so now we're going to go ahead and start solving it. So we take our derivative, both sides implicitly with respect to time. So dA dt equals 1/2, and now you want to be very careful. This is a product, that is B, and it's hard to see, B times H. So we're going to use our product rule. So if I let F be B, F prime will simply be dB dt, and if I let G be H, G prime will be dH dt, and then we just do our product rule where we're crisscrossing. So we're going to have 1/2, and I'm going to keep that constant outside for now, and derivative of the first times the second plus derivative of the second times the first. And remember, it doesn't matter what order you do those in because it's plus. Okay, and if you want to clean it up and distribute the 1/2, you can, but there's no need to. We can go ahead and just substitute in. So dA dt is what we're trying to find, so we're going to leave it there. Equals 1/2 times, and then we have dB dt is 5 times H, which is also 5, plus dH dt, be careful, this was negative 12, times B, which was positive 12. All right, and so dA dt, when we work all of that out, we're going to end up getting negative 119 over 2, which is also negative 59.5. And it doesn't matter. You can leave it. I usually just leave them as fractions so I don't mess up switching them into decimals. especially if I don't have a calculator. So it does not matter which way you do it. These are fine. And on your homework and all, unless you're told otherwise, you can use your calculator to help you with the arithmetic. Okay, we need units, and this is area. So this is going to be feet squared per second. So be very careful with your units. Okay, and so now you're going to write a sentence. And this one did just ask at what rate is the area changing. So you need to interpret your answer here. So we would say the area is decreasing, and we say decreasing because our rate of change of area was negative, is decreasing at a rate of, and then you choose either one. I'm just going to do negative 119 over 2 feet squared per second. But of course you can use the 59.5. Oops, oh, look what I did. Don't put that negative in there. That's my bad, sorry. See if it'll let me erase it. We don't want it to be negative because it's, because we said decreasing, so be careful with that, okay? The area is decreasing at a rate of 119 halves or 59.5. Okay, so leave that negative out because we took care of it. Okay? All right, we got another example. Example 2 is an airplane flying on a flight path that will take it directly over a radar tracking station. If the distance S between the plane and the tracking station is decreasing at 400 miles per hour when S is 10 miles, what is the speed of the plane? So what we have here, I'll draw a little picture. So we have an airplane. Oh, and you know me, I can't draw. So here's the airplane. We'll have wings, something like that. Okay, that's not too bad, I guess. And then we have the tracking station's going to be down here. I'll just make it be a little building. There's a little airport. Okay, so we have the airplane is flying, it's flying this way, and it's about to go over the tracking station. Okay, but where it is right now is it's above here, and we're going to measure that point that it's above, and it's going to be perpendicular. So there's our right triangle. Okay, so the distance between the plane and the tracking station, is this diagonal, and it is decreasing at 400 miles per hour. I'm just going to call this distance S, as it says in the problem, so then the rate would be ds dt, and it is decreasing at 400 miles per hour. It is decreasing, so that would be negative 400 miles per hour. All right, so we want to know what is the speed of the plane. All right, one thing I left off, and I'm sorry, the problem did tell us when I typed it in, I left it off, that this plane is 6 miles above. Okay, so an airplane 6 miles up. Okay, sorry about that. So there's our height there is 6 miles into the sky. Okay, and then we don't know where this point is right now, so I'm just going to label it X. All right, once again, it's a right triangle, so we are going to use our Pythagorean theorem. So the hypotenuse is S, so S squared will equal the height squared plus that horizontal distance squared. Okay? I can go ahead and find this distance because I know from the last problem that I'm going to end up needing to find it to put it into the derivative. So I can go ahead and find X. So we'll have to use the part of the problem that tells us that the distance from the airplane to the tracking station is 10 miles. That's our when, okay? And our given is the speed at which the distance is decreasing. So that's that negative 400 miles per hour. And we are being asked to find the speed of the airplane. That would be its horizontal speed, so that's going to be dx dt. That's what we're trying to find. Okay. So find dx dt when s is 10, given that ds dt equals negative 400. All right, that's a little messy, sorry. All right, so let's take our derivative. 2s ds dt equals 2h dh dt plus 2x dx dt. So we know that s is 10 and ds dt is negative 400, and we know that h is 6, but dh dt, the height of the plane is not changing. The plane is flying horizontally, so its distance to the earth is not changing, so that's 0, plus 2 times x, and all that talk a minute ago, I forgot to actually find x, so let's go ahead and do it. So 10 squared equals 6 squared plus x squared, so that's 100 equals 36 plus x squared. 64 equals x squared, so x equals 8. So this is all happening when the plane is 8 miles out from the radar station. Okay, so that's going to be 2 times 8 dx dt. Sorry about that, got myself sidetracked. Okay, so now let's go ahead and calculate everything that we've got. So 2 times 10 times our negative 400, that's going to be negative 8,000 equals, that's not an equal sign in front, that's a minus. Sorry, I cannot write on this thing. 0 plus 16 dx dt. And then when we solve, we're going to get that dx dt equals negative 500 miles per hour. Okay? Now, once again, we have to be extremely careful because the problem didn't say what is the velocity. And since this is a negative quantity, that is velocity, not speed. Speed is always positive. Velocity is speed with direction. It makes sense in the problem that this velocity is negative because x represented the distance horizontally between the plane and the radar station, and the plane is getting closer to the radar station. So that distance is shrinking, therefore the velocity would be negative. But we have to answer the question the way it's being asked, and it's asking what is the speed. So we've got to answer the question in terms of speed. So what we would then say is the plane is traveling at a speed of 500 miles per hour. Okay, and you've shown me the calculus, which gives me the velocity. So you're going to get a point for that. But then you're going to get a point for then answering it in terms of speed. If you left it just as dx dt equals negative 500, you're going to end up losing a point or two because you haven't interpreted it and answered the question with that nice little sentence. Okay, so be careful with these. All right, let's do one more. So here we have a television camera at ground level filming the liftoff of a rocket that is rising vertically according to the position equation s equals 50 t squared, where s is measured in feet and t is measured in seconds. If the camera is 2,000 feet from the launch pad, find the rate of change in the angle of elevation of the camera at 10 seconds after liftoff. So I hope you see that why drawing a picture is so important on these, because you got to figure out where everything is supposed to go. Okay, so let's look at this. So we have a camera and we have a rocket ship, and I could not begin to draw a rocket ship, so we'll say that here's the launch pad. Okay, so the rocket's going to be taking off vertically this direction. Okay, so it's going to make a right angle. And the camera is somewhere out here, and yeah, I probably couldn't draw a camera either. All right, so the camera's out there. Okay, and so we've got this, and the camera is facing up to the rocket, and there's an angle, theta, right in here, that is the angle of elevation from the camera up to the rocket ship. Okay, and the rocket, is going to keep going that direction. All right. So let's see what the problem tells us. So the rocket, the position is determined by S equals 50t squared, and that's the height of the rocket, okay? And the camera is 2,000 feet from the launch pad. So we want to find our when is 10 seconds. So we can find S, the position, by plugging the t in to the position equation. So we'd end up with S equals 50 times 10 squared, so S equals 5,000. And of course I've left myself no room, so I'm going to actually just write that crooked here, 5,000. Okay, so that's how high the rocket ship is at the particular moment in time that we're trying to calculate all of this. Okay, so we want to find not the rate of change of sides or anything like that, but we want to know the rate of change of the angle of elevation. So we want to find d theta dt. And you don't have to use theta, you could have used a different letter, that's fine. But we want to find it when t equals 10 given, right? You don't get points for writing given this and when that. It's just a way to organize it and to help you with that. So don't panic because, is this given or is this when or, all of that. It's just trying to help us be organized. So, all right, let's work it out. Now, we have no equation. This is a right triangle, but it's different because it's not asking about those side lengths. So we can't use our Pythagorean theorem for this. What we need is a relationship between theta and the quantities that we know. Well, we've got theta, and then we have the opposite side of theta and the adjacent side of theta. So what we have is the tan of theta is going to equal, now be careful, if I stick in there that the tan of theta equals 5,000 over 2,000, all that's going to do is give me a quantity that's going to go to 0 when I take the derivative, and I am going to not have an answer when I get done. So what I've got to do is use my variables. So the opposite side, which is the rocket's height, we're using S because that's what the problem called it, was S. And then I'm just going to call this bottom value down here B for the base. Okay? So tan of theta equals S over B. And now we're ready to take the derivative. So the derivative of tan is secant squared theta. And then remember that it's the derivative of the top, which is ds dt times the bottom, minus the derivative of the bottom times the top. All of that over the bottom squared. So there's our derivative, and we need to start plugging things in. And I did forget one thing, because I forgot it in my notes too. So be careful. Hopefully you're learning something by my mistakes. This is secant theta d theta dt. Be careful. And you would have realized it because no place in there a minute ago would you have found the variable you're trying to solve for. So be careful. It's really easy with these to miss some of those notation issues. All right. So secant squared theta d theta dt, we don't know what any of that is, equals, all right, ds dt. Well, what is ds dt? We don't know yet, but we have what S is. So I'm going to use this to solve for ds dt. So ds dt equals 100 t. You could say dt dt, but then that would just be itself, 1. So, okay, so when we solve for this, and we're doing this when t equals 10, so we get 1,000 for ds dt. So that's going to be 1,000 times b, and b is 2,000. These are going to be some very big numbers, minus db dt, b being the distance between the launch pad and the camera, which is not changing, so this is just going to be 0. I could type in times 5,000, don't even, or write it in, but don't even have to because the 0 is going to go away. And then times b squared, so 2,000. Oops, that looks like a 60, but that's 1,000 squared. All right, so remember that I said in our notes that we want the thing we're trying to find to be the only variable left in the equation, if possible, which means I need to figure out what theta is. So that we're going to work on that right now. And that, it's not hard, but this one you just have to really think about your trig, okay? So if you go in, I find it easier, or the easy thing to do is to come back up here. So I know that tan theta at the moment at which I'm trying to know what theta is. So that's the moment when the height is 5,000. It's when t is 10, and so the height would be 5,000, and the base is 2,000, of course. So then that's going to be 5,000 over 2,000, which is 5 over 2. So theta is going to equal the tan inverse of 5 over 2. That's just 5,000 over 2,000 simplified. And then you would use your calculator to get that. And I ended up getting that that's approximately 1.1902. And you'll want to, the best thing is something like this you would actually have to do on your calculator, and you want to go ahead and store it on your calculator. And if you don't remember how to do that, just ask me in class tomorrow, and I'll show you on your graphing calculator how you can store that figure. One thing that AP lets you do, which is nice, is you could now call this maybe A or something, some other variable. And so as you're working, then you wouldn't need to keep writing out these big long numbers. You could then use that letter in there if you wanted to, okay? So let's go ahead and substitute this in and finish out this problem. So what we have is we have secant squared of 1.1902, or you could write it as A or whatever letter you signed if you want to. And then d theta dt equals, and when you work all of this out, you get this really very large number, and it ends up being 2 with a lot of zeros, 2 million over 4 with a lot of zeros. Okay, and those zeros will cancel out, and that's nice. So it actually ends up being just 1/2, that whole value is. So then you want to solve it for d theta dt equals 1/2 divided by secant squared, and for room's sake I'm going to write that as A since that's what I had assigned it. And when you calculate that out with your calculator, you get 0.0689. And then because we worked in radian mode, we would write radians per second, because those are our units, radians per second. So what this is telling us is that when the camera's 2,000 feet from the launch pad and it's 10 seconds after liftoff, then the angle between the camera and the ground, that angle of elevation, is increasing at a rate of 0.0689 radians per second. And that makes sense considering the drawing and what's happening with the rocket. All right, that's it. That's all of our examples. If you have any questions, just ask me in class tomorrow. Good night.